Yesterday, we have seen article for function random variable. By using the definition, we proved basic theorems. Theorem number 1 says expectation of some random variables is equal to sum of separate expectations, and this can be for any number of. Theorem number 2 says expectation of product is equal to product expectations, but it is true under the that variable study should be dependent, whereas number 1 is true for any type of random. After that, we have seen simple example whose definition verify this theorem. Expectation of x plus y equal ex plus ey. Yesterday I had given you definition of covariance as well as seen property of change of origin and case covariance. It is of that covariance is affected by scale but not affected by origin. So adding a constant in the original data does not affect the covariance, but by some critical and covariance will be affected. So this is the statement which says to you covariance depend on multiple factor on addition of the constant. That is easily the right hand side. Today we are going to study again one important result, variance of linear
Excuse me, sir.
combination. Yes,
Sir, some students are not able to join the lecture.
it is everything like this. They should join before my start. It gets disturbance to me. Our lecture start at 15. Is it okay? They able to join? Start my class, there were 6 students. Now only 2 students are. This thing happening, people. Who is in the queue? Those are in the queue, you can ask them. For joining them. I this. Somebody can give the risk in the queue to join. Okay. Now anybody? Oh, shall- Fatima Maksud was there. Now again she joined. I the students are leaving the class and then again coming. We have 56, near about 56 students in our class, and only 13, 15 students are attending the lecture. Okay, anyhow, I will start now. Can you see the screen? Everybody can reply.
Yes, sir.
Okay. So we'll try to a very important topic, that is variance of linear combination of random variables. The statement is variance a x should be capital plus b y should be capital equals a square variance of x plus b square y plus a code, where small a and small b arbitrary constants, may be negative, may be positive. So this is the statement which is called as variance of linear combinations. This is very important to solve many type of MCQs. Let us see how to prove it by starting on the left side. Variance of ax plus by is value ax by minus expectation of plus by whole bracket square. The original definition of first semester, where equal expected value of x minus ex whole square, x by ax plus by. Expectation bracket by minus expectation inside, so minus ax minus by. Now I combine the simple terms together, ax minus time ax as plus by minus e of b bracket whole square. Now here a is a constant, you can take side. So curly a x minus ex curly bracket come Another curly bracket, B is common, y minus ey, square bracket is overall, square it. I formula of A plus B square. So expectation square of this curly bracket plus square of this curly bracket time product of these two curly brackets. That is formula A plus B whole square. Now I use expectation inside for three terms. Square taken inside, so A square is pure constant taken out. Expect value of x minus ex square plus b square out because it is a constant. Expectation of y minus ey square plus 2a multiply b. This is the product. So twice expectation for of these two curly brackets. Now easily you can see from your semester 1, it is a definition for variance of x. This is a definition of variance of y. And just now, it's given you definition of variance. X minus ex multiply y minus ey. Be careful, this is minus. So this is your covariance, and that proof of your statement. This statement can be written other way around, plus as minus. So you will get variance of a minus by equal to square variance of x plus square variance of y. You have to remember this important part. It is a minus, variance will be minus. If it is plus, covariance will be plus. 2, if x and y are independent, then variance of x plus minus by becomes a of x plus b square variance, because independence, yesterday I had given you the remark, covariance becomes 0. So this, if the variables are independent. Now we proceed ahead. A new topic, correlation coefficient. All the technical names parallel to paper 1, but method of calculations are different. It is treated as a population correlation coefficient, whereas what you studied, that is treated as a sample correlation coefficient. That is a basic difference between paper 1 and the correlation coefficient between bivariate discrete random variables is given by CR, short form of the correlation coefficient between x comma y, is a C for paper 2, x y script. In paper 1, it is denoted by small r. Whereas in paper 2, correlation coefficient denoted a Greek symbol, that is rho xy. So that is the difference in the notation. The technical way of in definition is common. It is a ratio of covariance to the standard and standard nothing but root of variance of respective variable. So it is covariance y divided by sigma y. The definition is exactly parallel for one. Way of calculations are different. You have results, remarks, correlation between xy, same as correlation between x. The relation between brother and sister or sister and brother will never change. So if I study the correlation height of father and height of son is will be same as correlation between height of son and height of father. So there is no change. The order of the variable alter. So it is commutative. Second, if the variables are independent, correlation of multiple choice question. Just yesterday I told if the variables are independent, covariance is 0. And definition correlation coefficient, numerator is a covariance. So it is quite trivial to justify remark 2. If and y are independent, covariance is and any number is 0 divided is 0. So under independence, correlation is 0. Yesterday also I said same thing in case of covariance. If between xy equal to 0, you cannot say variables are independent. There is a numerical example to justify this concept. If you have a book with you, you can open the book and you can see there is a clear example. Numerical relation of xy 0, but the variables are not independent. You can go through it. Third remark, correlation of variable with itself is a perfect relation. Answer always 1. Remark number 4, correlation of x with opposite of x minus x. Perfect opposite variable under study, correlation coefficient -1. You have repetition values of correlation coefficient. By using this formula to the given bivariate data x and y, you calculate coefficient, and after calculation you have to make comment, you have to interpret. So the interpretations are rho greater than 0, then is variables are calculated. Rho less than 0, variables are negative correlated. This word should be there, negatively correlated. If rho equal to 0, then variables not having linear relationship. What understanding this rho, that formula is used only to study relation. Rho equal to 0, you can say X and Y not linearly related. That means there may be another type of relation between X and Y that may be non-linear relation. So correlation coefficient is used to study only linear relation, not curvilinear. Rho equal to 1, inter perfect positive correlation between Y. If rho equal to -1, then there is perfect negation X and Y. What is meaning of perfect? It means if is, then Y has to be in same, that is called as perfect positive. What perfect negative? X increase and it has an impact on portion variable Y opposite direction. Increases, then Y decreases same amount, that is called negative. Interpret rho greater than 0, rho less than 0, only positive. So you don't have about the relation of x, y. Or if x increase, y also increase. There sometime x increase but not increase. That's why perfect word is not used here. When it is +1 or -1, you have a guarantee. X is increase, y has to increase. X is decrease, y has to decrease in the same proportion. That's why perfect positive, perfect negative. We have certain properties to study correlation coefficient. Just like I had given a definition of covariance, property, change of origin and scale, and it is observed covariance is affected by scale, not by origin. In the same guideline, we have effect of origin and scale on correlation coefficient. Statement mathematics: the relation of x plus b, comma cy plus d equal c divide absolute of ac to relation of xy. If you state there is numerator AC, denominator also AC. But in the denominator, we take positive value of product. Suppose A equal to -2 and C equal to, the numerator will be -6 and will be +6 because absolute means negative value or positive value are giving a positive number, absolute. So numerator is -6, denominator is +6. 6 get cancelled and remain. So what the statement says, correlation does not affect numerically by origin and scale. The magnitude of correlation is same, but sign will be affected the sign of scale. If both scale has similar sign, correlation remains same. If they have opposite sign, the new correlation will be opposite of old correlation. So this statement can be written in this way. The magnitude correlation does not affect by change of origin and scale, but algebraic sign is depend on sign of scale. Just now I told, suppose I write x plus 5. Here I write minus 3y plus 7 variable. Answer will be 2 multiply minus 3 divided by absolute 2 multiply minus 3. Role of B, no role of D. It is not depend on the, only depend on the product. So if original correlation is 0.8, the new correlation will be minus 0.8. So magnitude remains same, only sign will change, and that sign depend on the multiplied factor in the proof is very easy. Let U equal AX plus V equal CY plus D. This U of origin and scale formation. Then correlation of U comma V will be covariance comma V divided by variance of U into variance of V. This is a definition to calculate correlation coefficient of new variable. Firstly, we'll get covariance of U comma V, which is proof of your yesterday's lecture. U replaced by AX plus B replaced as C. This Y should not be there. It is mistake. Drop it. So this is the AC covariance. You have to see the proof from yesterday's lecture. Variance of U AX plus B not affected by addition, so you can drop. Immediately you can drop, and it depends on multiplied come out where variance X. You have a proof in semester 1. Similar of V square variance, put 1, 2, 3 in equation 1. So correlation coefficient between U and V equal AC time covariance of X comma Y, A square variance of X multiply B square variance of Y. This is B. It is mistake, it is B. Sorry, it is C. C time YD. So this there. So now A square from the root come out mod A, C square come out with E, because when you take a root, plus minus probability. But variance is a positive root, that's why modulus sign. Mod A multiply mod C is mod of AC, absolute of AC. And what is this balance? This is a definition. coefficient between variable x, y. So finally you get correlation B comma C plus D equal AC divide absolute AC times correlation of xy. Property number 2. The correlation coefficient always lies between -1 and proof. Suppose I new variable u x minus ex divided by sigma x. V equal I minus ey divided by sigma y. Then I take expected value of u plus minus whole square greater than equal to 0. Why I write like this? Because you are taking expectation of a square quantity, and square never indicate negative, always positive number. So expect positive quantities. I apply B whole formula, square of u square e plus minus 2 times product, that is school result. Now take expectation inside e of u square plus e of square plus 2 times e of uv. Expected bracket for each term, only quantity out greater than equal to 0. Now replace u, replace v by your definition. So expected value x minus ex by sigma x square plus expected I minus e by sigma y squared plus minus 2 expectation 2 into now sigma x square will separate x into sigma y. This is positive from is greater than equal to 0. Expect x minus square is a variance. This is a variance of y, and this is a. So what you get, sigma square x divided by sigma square x cancel, get 1. Sigma square cancel with sigma square y, you plus minus 2. This is a covariance by sigma x, sigma y from the result. Now, if you look this, it is your correlation coefficient. So plus 1 is 2, plus minus 2 rho get that equal to 0. For this equation 1. We are doing what purpose? To correlation coefficient is between -1 to 1. That we want to prove mathematically. Now I take from this equation and the condition. So from condition 1, consider 2 plus 2 rho greater than equal to 0. Take this 2 on the right side. So 2 rho greater than equal to -2. It is multiplied, divide on the right side. So rho greater than equal to -1. This is your equation 1. Now from 1, take a minus sign. 2 minus 2 rho greater than equal. Take this minus 2 rho on the right hand. So 2 rho 2. Now 2 get cancelled. Rho less than 1. This is your second equation. First says rho always and say rho always equal to 1. If you combine A and B, you get a proof of correlation coefficient as a property. Property number 1 says correlation coefficient does not affect by origin and scale. Magnitude same, but sign on sign of scale. If both scale are the same sign, correlation remains. If scale are up, one is plus, other plus, so new correlation will be opposite of old correlation in the sign. For example, if original correlation is 0.8 and scale having opposites, then new correlation will be 0.. Theoretical question on the top. Find correlation coefficient of bivariate discrete random variable and with usual notation prove that correlation coefficient lies between -1 and +1. We'll try to see one numerical example and then stop today. Better to take numerical example to understand what I given today. Let xy has joint probability distribution. Compute covariance x comma y, variance of x, variance of y, correlation of x comma y, correlation between 2x plus 3 minus 3y with this as a bivariate probability distribution. This is your problem. In exam, you will get this idea for calculation purpose. But in exam, you will be having much. For this bivariate table, you have to get covariance, variance of xy, and so on. You can, when I taught you previous chapter, total in front of x is marginal probability of x. If I of columns that represent marginal probabilities variable is values for y. So probabilities for single y. What is the reason of calculate this? If you get a marginal, then you can find x of x, variance of x. From these and values, you can get the value of y and variance of y. And to get a covariance, you require this inside all values type of calculation. Variance of x comma y is by definition expected value minus expectation. Recall my yesterday's lecture. I had given two definitions for covariance. One is original and other is simplified. And I told at that time, original is useful for theoretical results. and simplified RAZ for calculation purpose. So this is the simple definition of covariance. So to get covariance, I have three calculations: expected value of X, expected value of Y, and then a product. What is X? From your semester 1 summation X into PX. X is 0 with this order. X is 1 with this probability, so it's half. Q of X is 1 by 2. E of Y, definition says E is summation Y into P. Value of Y, multiply probability as a 1 multiply probability 1 by 8. 2 multiply probability 2 times half. Simplification is 4. E of xy. Now under expectation, two variable E replaced by two sum. That is the logic. What is inside? It may be anything, put it inside. Multiply joint probability. Start. X having two values, Y has total calculations 2 multiply 3, 6. 6 pair. But it is a product. So X is 0, Y is 0, result is 0. X is 0, Y is 1, product multiplied 0 is 0. X is 0, Y is 2, product is 0, 0 multiplied product is 0. So first calculations become 0. Multiply is 0, so this is also 0. Now 1 multiply 1, product is 1 and joint product is 1 by 8. So 1 multiply 1 by 8. 1 by 2 is 2 and joint product is 1 by 4. When I speak for two variable, it is the joint probabilities. 2, 1 by 4. Simplify, it is 5 by 8. Therefore, covariance of xy 5 by 8 minus half 9 by 8. Simplify the result of covariance. I want variance of x, expected value of x squared minus square of expectation. This is to simplify, not original variance definition. You have knowledge of Ex from previous calculation. Just get E of x squared. E of x squared is nothing. E replaced by x squared into px. First value of x is 0. Multiply anything is 0. Second value of x is 1. 1 square into product is half. Result is half. Variance of x, E of x square is half minus Ex square. Multiplication 1. Similarly, you can get where expected value of y squared summation y squared p r. When you writing expectation of y, everywhere be y. First value of y is 0, 0, anything is 0. Second one, 1 square multiply probability of y equal to 1 by making a total plus sign. Y equal to 2, 2 square multiply probability and simplify 7, 8. Therefore, variance of y is expected value of y squared minus of expectation. This is the simplification. To get a correlation, XY definition says covariance of x comma y, root of variance of x into other root variance of y. Everything is with you from previous calculation. Put the numbers. Right answer. This is your correlation coefficient, which is a positive. That means the variable x and y positively correlated. The interpretation, if x increases, y also increases, and so on. The last bit, correlation of 2x plus 3 minus plus 7. I will apply this is multiplied factor 2. This is multiplied factor 3. So property says AC divided by absolute of AC into correlation of XY is minus, this is plus 6. Cancel. Original correlation is this much. Scale has sign, so correlation is minus of. So that is the proof of property change and scale. Interpretation, this is wrong. Why this is wrong? Because original correlation of XY is positive. But this new variable, you can call this as U, you can call this as a V. So you have U and V negatively correlated, not XY, because original variables are correlated. And the new variables defined by these transformations, they are negatively correlated.